that's what we'll be talking about today. Before we start, any questions? Problems on assignment 1? Ready to move on to 2? Excuse me? Okay. All right. Let's talk about doing multiplication by addition. By observing that 4 times 3 is really the same as saying 4 added 3 times. So we can write our own multiplication program, which I'll call mult1. Notice that I'm dropping out the lambdas today. Okay? They're here. The lambdas are here. We're just using the syntactic sugar to get around them. Not get around them, but just a shorthand, really. Okay, we're going to define mult1 of xy. Just to, one last time, let me just write it over here. So that's the same as define mult1 lambda xy. Okay, just one last reminder. Okay, so let's define mult1 of xy. Well, if we look at this 4 times 3, so this will be our x, that'll be our y. Well, this is really the same as saying, let's add 4 to the multiplication of 4 times 2. And then 4 times 2 is plus 4 times 1, with our base case being what? What should be our base case in this process, in this procedure? If we're adding some number of times, when do we end? Right, when y hits 0. What do we want to return? 1, 0. We're adding, right? So when you're adding, you use a 0. You're multiplying, you use a 1. Otherwise, we're going to add x to mult1 of x minus y1. Mult plus if define. This code is on the handout for today.
Yeah, there's one missing on the handout.
Oops, sorry about that. Yeah, in the code, it should say plus x mult1 x rather than mult x. Apparently I changed the name after I ran the code to make sure it ran. Okay, so let's look at the substitution model for mult1. Let's evaluate mult1, 3, 4. Okay, let's do this a little more informally than we were using the substitution model yesterday. So 3, 4. Is 4 equal to 0? No. So we have plus 3 called to mult1 and 3, 3. Good. So what does mult1, 3, 3 become? Mult1, 3, 2. Okay, need to continue evaluating. Mult1, 3, 2 becomes plus 3. Mult1, 3, 1. Mult1, 3, 1. And finally, we hit our base case. And we can start building back up. once again hitting the bottom of the board. See the shape? Yeah.
Could we have saved a step by making our test case if y is 1 and then returning x?
Okay, if we changed y equals 1 and then changing this to x, could we have saved a step? Well, we could save a step, except that we now can't multiply by 0. We have no hand like that. Okay. Okay, we delay some operations. We go out and we come back in. These operations are deferred until we've computed down to our base case. A process having this shape is a recursive process. And what a recursive process means is that there are delayed operations. Don't confuse recursive process with recursive procedure. A procedure is recursive when it calls itself. That's a recursive procedure. But a recursive procedure need not generate a recursive process. And we're going to see in just a minute how we can have a recursive procedure that generates a process that we'll call iterative. Okay? Not every recursive procedure has delayed operations. How many delayed operations do we have?
Y.
So there are y delayed operations. And how many steps does it take in terms of y to compute this answer? 2y. 1 to expand, and 1 to come back down. Okay, so let's talk a little bit about some formal notation to denote how long it takes in time and how much space it uses.
What is in the computer's memory throughout all this?
What is in the computer's memory throughout this? When we make this call, these delayed operations are pushed onto the stack. Okay, so the computer has a stack, it's memory. This is pushed onto the stack and it goes to evaluate this. When it goes to evaluate this, it pushes this on the stack, which is now on top of this, and goes to evaluate this. When it goes to evaluate this, it pushes this on the stack. So that's what we're talking about in terms of space. We're talking about memory space. How many operations are we saving on the stack? In this case, we're delaying y operations. We're taking y amount of space on that stack. The formalization for orders of growth is let's say that we have n, which is a parameter that measures the size of the problem. On the right-hand board, we were using y. Okay. Y was the parameter that was measuring the size of our program over there. R, then, is the amount of resources required. The two that we're going to talk about are T of n, time, and S of n, space. But we could talk about things like how many primitive operators are we using, how many register locations are we using on the computer. We could measure other things other than time and space, but we're going to focus on time and space. We say that Rn has order of growth theta n, which we can denote by Rn equals theta n, if there exist positive constants K1 and K2 independent of n such that K1 f of n less than or equal to R of n less than or equal to K2 f of n for any sufficiently large value of n. And you guys thought the math was gone. So what does this mean? Well, what's space n and time n for this procedure? Well, we talked over here that there were y-delayed operations and 2y operations. Let's change that to n, because we're going to use n as our measure. So there were y-delayed operations, it's theta n. In time, we had 2n, but the constant drops out.
How did we get an F in there? What are we defining the function as being?
Sorry, we have order of growth. I missed the notation up here. Theta f of n.
It's also an if and only if. You say if there exists, it's if.
So what we're doing is we're bounding f of n on both sides of our resource. There are other notations that you only bound on one side or the other. This is a more strict one that causes us to bound on both sides. If we only went this way, we could pick f of n of n squared. We could pick f of n much larger, because it'd be less than or equal to. So this is forcing us to pick between the bounds, bringing us down. When you say something is theta n, you're talking about that. That's linear. Okay, so we would say that this is linear in terms of space and time. That is, let's say, so we're measuring n, our y here is our measurement. If we go from y being 5 to y being 6, how many more steps do we expect? One more, right? It's linear. As we add more and more, we only get one more in proportion to what we've added. Let's look at some more examples to look at orders of growth. Let's look at mult 2. Yes?
Would that, I thought we decided it was taking 2 y steps to complete the process.
Okay, it is. But when you say, you wouldn't write theta of 2n, because as n grows large, the constants don't matter. The constants come out here into these expressions here. So the 2 would be part of this constant out here. So we take the constants out of it, and we only measure in terms of n.
Okay.
The constants pull out.
Geometrically, you can draw two straight lines through the origin representing K1 and K2, and your curve always has to be between those two lines.
Yes. I'm a computer scientist, not a mathematician. But if we had 2 lines here,
They're not necessarily going to be straight.
right. If it's linear, they will be, though. And then f of n falls somewhere in here. So they'll be straight if we have a linear curve. Well, not curve, that's line. Let's look at mult2 and start looking at some more. Mult2 also takes x and y, but is written slightly differently. It has a procedure defined within it, our block structure, called mult-iter. Which takes a y and a variable called ants. If y is equal to 0, we return answer. Otherwise, we call mult-iter on y minus 1 and add x to our answer. And then make a call to mult-iter with y and 0. So what we're doing here is on every time step, rather than delaying an operation, we're adding x to our answer. So we're not delaying any operations. We're using a state variable called ants to keep track of our partial solutions. So if we follow this, we say mult2 on 3, 4. Well, that results in a call to mult-iter for 0. Why am I not passing mult-iter x? Why am I not passing in our x to mult-iter? Why am I not doing that?
Because then we wouldn't be able to keep track of when we're supposed to stop, what our answer is.
X itself doesn't change.
Yes. X doesn't change. X is scoped here. So we can actually use x here because it's scoped in this procedure around it, and we can use that. We don't need to actually pass it in as in our mult-iter procedure. We can use it scoped. So our call to mult-iter y0, 4 is not 0, so we call mult-iter minus y1, 3, plus x ants. Answer is 0, ants is 0, x is 3, giving us 3. Next call, well, this is not 0, so we call mult-iter. Yes, x would be the new x that we've created. The x on this external one would have been pushed onto the stack, and a new binding for x would be created. But because we didn't do that, that binding of x is still available to us because it's in a procedure that we're scoped by. Okay.
Say that again, please.
Because we haven't redefined x, this procedure here is contained within this procedure. So it's scoped within this one. Which means that this one here can use any variables that are available in this external procedure, barring the case where, as it was just suggested, what if we had redefined x? If we had created a new x, then within this procedure, our new x would apply, not the external one. Which is why sometimes when you're writing procedures like this, it helps to change the names of your variables. We could have easily called this counter, which would have eliminated some scoping confusion, because the y inside here is locally scoped to this procedure. It's not the same as this y here. When we get into the environment model, we'll see a lot more of how we have these variables in their own environments. Each procedure creates its own environment, and we'll go through that in detail. Other questions?
When we're counting up processes or whatever, when we're counting up steps here to compare this, say, to the recursive method, we don't count the little additions and subtractions in there? Or we count these?
We're going to call those, basically, we're going to consider those to take just sort of unit time, that they don't take, that we're going to assume that these primitives take unit time, that they're not anything that's spinning off and creating something that takes, you know, linear time in and of itself, or more time. We're considering that those are just unit operations.
Isn't that all we had in the other example, though? In recursive?
Sure.
It takes some finite amount of time, but it's not effective.
Right. I mean, it's, you know, it might double it or triple it. There's some constant factor that we're adding on. But remember, in this notation, we can drop the constants, because those are pulled out as the values of K2 and K1. The constants go away.
This ended up with a smaller time, smaller order per time. Doesn't actually mean that it's faster.
Well, actually, does this end up with a smaller order for time? How many steps in terms of n? In this case, our y is our n. Well, for every n, we need to do a step, which is still theta of n. It's still the same order of growth.
But this time they're not the primitive additions. Is that right? They're multi-iter things that
It's just another call to this, to this, to this. Right? And we are doing a primitive, there are primitive operators within that call. Right? We've kind of been going quickly over the substitution model, so I haven't been going through every single primitive operator, but we've certainly been doing primitive operations. We just didn't delay them.
Well, we didn't count them either, or we wouldn't have said there's two y steps, right?
Right. In that case, I wrote everything out. But again, the constant doesn't matter.
Okay.
Which may be rather unsatisfying, but the constant doesn't matter when we're talking about a linear process, because as n gets,
Yeah.
you're just measuring the amount of time.
Yeah, I guess that's a constant.
You're worried about what happens when n grows large.
Right.
I'm just comparing the two problems.
Space? Smaller, good. If n is 1, 100, 1,000, a million, is it going to change anything about the amount of space it takes? Am I going to be pushing anything onto that stack? In this case, we say space is constant. We denote that by theta 1.
When you keep calling yourself to get down to the answer, don't you have to pass that answer back up?
No.
You don't?
No, because it's right here. We're passing it answer plus x. So we're updating answer at every step. And then finally, at our base case, we merely return the answer. We're not delaying any operations. We're adding to answer every single time we call multi-iter. So there's nothing to pass back up. So we just call and then return the state variable. A process that has constant space is known as an iterative process. Has no delayed operations. So this is when I was talking about don't get confused between recursive process and recursive procedure. Because multi-iter does call itself, multi-iter is a recursive procedure. However, it generates an iterative process. When we're talking about the process, we're talking about the amount of space we're taking up. A recursive process delays operations. An iterative process does not delay operations.
Does the interpreter really not treat this recursively? So I can't put an additional statement under the multi-iter because it will never get back there. I mean, logically looking at this...
You mean if you wanted to have another statement in the body here?
Will it ever get there?
No, because it's going to, well, what would happen is, in this case, it would return answer from the if at the base case, and then it would come down to that statement.
So it's not going to recurse out and hit that for each one on the way out. It actually is.
Right, because this isn't delaying any state here. So when we had the recursive thing here, the delayed operator was here, and we were building back up. And here, we just add to our state variable. We're not delaying anything. There's nothing being held from that particular call. When we call multiter this time, we call again, but there's nothing else waiting there.
It's still, is the interpreter not building up a stack of function calls in this case? Is it really calling, it's getting rid of the old version and...
Scheme is something called tail recursive. Unlike C, Pascal, and other languages, which means, officially, if I could find the real definition that I wrote down. Maybe not. In any case, it means that it's not saving state. Can't find my notes. There we go. So, tail recursive means that it executes an iterative process. In constant space. Meaning that it doesn't keep stuff around from those calls. It doesn't build up stuff on the stack for every single procedure call. Once it's done with this procedure call, if there's nothing hanging around, it's gone. Unlike C or Pascal, where things stick around. Yep.
But it still seems, to follow up on that point, it seems like if there was a statement after the function call, you would have to go back and check if there's anything after that. It would kind of go back up. Right?
It'd no longer be tail recursive.
Right, it wouldn't be a tail recursive, it wouldn't be an iterative process at that point. I guess I'm having trouble with the question because I can't imagine a case where I'd want to put a statement after that if. In this case, where I'm writing this process, there's nothing that I would want to do afterwards. I've returned that answer. There's nothing that I would delay till later.
But the interpreter would not know that because that wouldn't be a need for, right? So you somehow have to go back and check if there's anything.
Right, and it wouldn't be tail recursive anymore because there would be state that it needed to save. Okay, so it would no longer be an iterative process at that point.
What sort of statement are we talking about that we're putting in?
I'm actually having trouble coming up with a sample statement there because I can't imagine anything that we would want to put there. All this procedure does is it iterates through computing multiplication for us. I love coming up with examples on the fly for you guys, but it doesn't make sense to have anything there.
I don't think it would execute a statement there anyway, because when return from multi-iter, it would come out with the statement below it.
No, and that would be the statement below it.
This would be the statement. This would be the next statement if. So we had one here, and then we'd have two here.
But that statement would already be executed by the time we got to the call for multi-iter, wouldn't it? It returns out of the function or the procedure. Why would you go?
Does the scheme interpreter optimize? So if it identifies tail recursive, it then does something different than if it doesn't?
Yes.
Okay.
But that means it has to look a step ahead. Right?
It recognizes tail recursive because of the way the last line is written. I explained something about that to me yesterday, that since the last line calls multi-iter without any thing acting on it, that it knows that it's tail recursive.
Well, I can go over this in this.
Yeah. Why don't we leave this recitation so we get through some more material right now? Let's look at a bunch more procedures and try to look at them in terms of space and time. Let's look at some more multiplication. Let's look at fast mult 1. Fast mult 1 of A and B. If B is equal to 0, 0. If B is even, we call fast mult 1 on double A and half B. Otherwise, yes, even B, sorry. Otherwise, we add A to the fast mult of A and B minus 1. And then let's look at fast mult of, oh heck, let's do 312. So our call, we go into the con, does B equal to 0? No. Is B even? Yes. We call fast mult 1 double A, half B. Double and half are defined on the sheet you guys have. We come back, make the call to fast mult. B is not 0 yet, but it is even. So we call fast mult 1 on the double of B, double A, half B. Fast mult 1, B is not 0 yet. It is not even. So we delay the operation of adding A, 12, to fast mult 1 of A, B minus 1, 2. Okay, fast mult of 12, 2. 2 is even. Fast mult 1, 24, 1. One is not even, so we add 24 to the fast mult. Space. So now we have plus 12 plus 24. B is now 0. Return 0. So we have plus 12, 24, 36. Note, we still have sort of a shape where you can imagine that this board was placed on top of that one. Goes out and in. So what type of process is it? Recursive process. However, we're not delaying an operation for every single n. In this case, would n be A or B for our function? How are we going to measure? Are we looking at A or B as our n? I hear A. Do I hear a B? Maybe? I hear A, I hear B. B is the variable that we're using to determine how many times we're going through. So our n is going to be our b. It's going to be b. But we're not doing one delayed operation for every b. And we're not even doing one step for every b. Effectively, what we're doing at every time step is we're breaking the work in half. Okay? And if we break the work in half, we denote this time as log base 2 of n. Okay, so you can think about this. When I say we break it in half, you think about a tree. Some number of steps, and this is our b here. This is the number of times we want to do something. We're actually doing this number of steps. So let's say this is n. What's the height of a binary tree with n leaves? Did you guys do this in September? Log 2n? Okay, so this is the amount of time that we're taking. How about space? Also log 2n.
And the fact that we're not truly breaking it in half for every step, I mean, for the ones where we just subtract one,
Constant.
it's not breaking it in half. But
It adds in as a constant value because you can actually calculate on a number how many times you're going to hit an odd. You start out with an odd, then you go even. Let's look at, yes, question?
The space here is log 2n. Now, how is that different from the previous one where I think the space was constant, you say?
In the previous example, so that would have been multad 1 or whatever it was, mult 2. In mult 2, what we were doing, wait, space constant, mult 1 had constant space, not mult.
Mult 2 and
You want to talk about the constant space, or you want to talk about the linear? Okay.
Mult 2, I think
Okay, mult 2 did use constant space. It was an iterative process. We're not using constant space here. As soon as we start drawing something like this, an out and then an in, which would look a lot better if it were down here. So that's kind of out and in. That's not constant space anymore because we've had to delay some operations. As soon as we delay some operations, we're outside of that.
But why is it log base 2? Why log n? You know, why would that be the order of that of the space? You're not expanding. You're expanding only like on the odd point when you have to.
Right.
Which the number of those.
But we are expanding.
How does
So we.
it equate inside? How do you get to the log n in that case?
If you think of these numbers and as binary numbers, the number of steps that you have to take is no more than twice the
Yeah, but
number.
if b was power of 2, you have that would be constant, right? Because then
Right, but we're looking at this. This is sort of the worst case analysis. Okay, you're talking if we have a power of 2, we're sort of looking at the best case analysis. When we're analyzing in terms of space and time, you're sort of looking at the worst case. You're looking at the bound for it. You're not looking for the absolute best thing that could happen. You're looking for when n gets really big and you're starting to get into your worst case. That's what your bound is for.
The worst case would be 2 to the n minus 1.
Right.
how does the fact that we defined half and double using multiplication affect that? Multiplication and division affect this? Won't it, every time we do that, cause another process which...
It depends how multiplication and division are implemented. If we called our multiplication by addition, and it's not a primitive one-unit operation, then certainly we would need to start considering how much time that took in addition to what we're taking here.
Okay.
But in this case, we're using the primitives for multiplication and division. We're going to consider those just be unit operators, that they don't have time n behind them or n squared or anything like that. Kind of process this one might generate. The other dead giveaway for that would be that I named the inner loop something like iter. cons equals B 0. Result even B. We iter on the double of A, half of B, result else we iter A minus B1 plus A result and then call iter on A, B, and 0. So let's look at this one. Let's call fast molt on 3 and 12, same as we used before. So what is this? What's our first call? What's the next line? Define. Iter on 3, 12, 0. Come into iter is B, second variable 0. No. Is it even?
Yes.
Right. So we say iter on double A, half B. Do we do anything to result? No. We call iter again. Is this 0? No. Is it even? Iter double A, half B, pass result. Come in. B is not 0. B is not even. So we call iter on A, 12 to 12. B is not 0, but B is even. 24, 1, 12. B is not 0 yet. It is not even. So we iter on A, B minus 1, A plus the result. B is now 0. We return the result. Nothing's delayed, straight down. Which means, in terms of space, this is constant. How about in terms of time? Let me log in. We're not delaying any operations, but we are breaking our work in half at every time step.
Is that log based too?
Yep. Mixed in with a parenthesis from below. Yes?
One could speed it up by finding the smaller factor and saying 3 would be easier to use than 12. But still, which one's the order?
Right. You could speed it up by deciding which one you're going to use, the smaller of the two factors, but it's not going to change the order of growth because then if you picked A instead of B, it's still the N. Right? It's still based on some counter. And the counter for our routine is always going to be whatever is here. So it's still going to be N.
So you don't say it's of the order of log 2 of the minimum of A and B.
No.
Okay.
You can, but we don't. And
For some problems you do.
Okay.
I didn't want to go quite so.
You would save chalk.
Chalk is cheap. Okay. I stole a toy from my child this morning who saw it on the table and was very excited and started playing with it, and then I shoved it in my bag and left. Very unhappy about that. So this is supposed to be Towers of Hanoi, so one could imagine that we had 3 pegs here, because I don't actually have 3 turtles. So we have Towers of Hanoi. Let's assume that there's a peg here and here. We want to move these from here over to here. So how can we do that? Are you guys familiar with Towers of Hanoi? You can't move a larger ring on top of a smaller ring. Okay, so you can move a ring to either of the free pegs with the condition that it can't go on top of a ring that's smaller than it. So, well, how can we think about this? Well, let's do some wishful thinking here. Let's say, well, if I could move these three to an extra peg, then I could move my big one to where I want to go. Similarly, if I could move those top ones off, I could move my next biggest one over. Then I can do this and this. Now, do you want to see if I really can do it? I practiced last night, but I'm sure. Okay, so we want to go. We're going to end up here. Yay. And then we're going to go here, 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 here. Here, here, here. Yay. Thank God there were only 4 rings. All right, let's write an algorithm to do that. And the turtle will go home to my child. Let's write a program to compute the towers of Hanoi. Alrighty. So, let's define a procedure called move tower. Which is going to take 4 arguments. It's going to take the size of the stack of the rings we still need to move, or we need to move. And it's going to take numbers representing the 3 pegs. The from peg, where things are, to where we want to go to, and extra, the number of our extra peg. So in that case, I was moving from the middle peg, which we could have called 2, to a peg which we could have called 1, with our extra being 3. So, if the size of the stack is 0, do we need to do anything? We're just going to return a nil. We haven't seen nil yet. So, nil is the empty value. Okay, we'll see nil when we start working on lists. We'll use nil. Nil is basically an empty list. This game. You should note that by nil, or some people write it as. But that's quote and list structure, and we haven't seen that stuff yet, so let's just ignore that for now. So we're just going to return a nil. We don't need to return a value here, because we're going to give our answers to our user by printing out the steps we're taking. So we're not returning any numeric answer. We're just going to return a nil. Otherwise, we're going to do 3 things. We're going to call move tower on a stack that's 1 smaller. That's my wishful thinking. So let's say I can move that smaller stack onto my extra peg, get it out of my way. And we denote that by saying move tower, and call it on 1 ring smallest stack. We're going to move it from the peg it's on onto the extra peg, using our 2 peg as our extra. Okay, the wording's a little bit confusing. Okay. So this is the peg that we're on. This is the peg we're moving to. This is the peg that we get to play with as our extra one. Okay, so once we move the smaller stack to that extra peg, we're going to print out and say print the move from 2. We're just going to tell the user we're moving a disk from our from peg to our 2 peg. And then we're going to move our tower, our smaller tower, back from this extra peg to where we want to go, which in this case was the 2 peg. So we're going to move it from extra to the 2 peg, using from as our extra peg. Do you guys want to put this code in, or we can get the code up so you guys can play with it and see what it's actually doing on the computer? Some number of parentheses. Okay. Print move is on your sheet. Print move is using display, which we talked about yesterday. This is one of those rare cases where it's okay to use it. We're not really returning numeric values. So we're going to define print move new line in parentheses puts a carriage return in your buffer. And then, excuse me?
It takes from a 2.
Oh, sorry, yes, print move does take arguments. So we're going to display move top disk from display from display the string to display to. This is just a little procedure that written to say where the disks are moving from. Because we're just printing out the moves. We're not representing any of this internally. When we make a move, we're just printing out to the user what they would need to do to make that move.
What is display quotation to?
So display takes an argument. It can either take a variable. In this case, we're passing it a string. It'll display the string. It'll take the quotes off and display the string. Okay. But this isn't the main focus. I just wanted to put it up there so you guys saw new line and display. Let's make it go away. It's on your sheet so I can erase quickly. So, Towers of Hanoi. Anybody have any sort of feel for what it's going to take in terms of space and time? Let me give you one example. And let's make it a really small example. So let's move tower. Let's make it of size 3 from peg 1, 2, 3. So it's going to go from 1 to 2 using 3 as my extra. So we come in here, size is not 0. So we're going to move the tower of size 2 from 1, 3, 2. And in this case, we do go back up here, and these are delayed, right? So we go off. We do our move tower on 2, which is going to be a move tower on 1 from 2, 3, which is a move tower. Oh, God. Should have picked a smaller number. 0 from, I've already messed this up, haven't I? From 1. Okay. It's now 0. We return nil. We hit this next statement. We print move from 2. And so we say move top disk from 1, 2, 3. This is just not going to trace out well on the board. Let's say we have, let's look at this in terms of, let's try to do this a different way. Let's say we're moving a tower. 3, 1, 2, 3. Let's do it this way. We're going to do a move tower on 2, 1, 3, 2. I'm going to print a move. And then we're going to do a move tower on 3 from the extra 3 to the 2, 1 from. This is going to work out better. Yes, all right. Yes, if we keep the size the same, we'll be here all day. So now we're going to move tower on 1 from peg. Let's see. So this is the from. So this is going to be 1, 2, 3. Print. Move tower of size 1 from extra 2. This is move tower 0 from 1, 3, 2. Print. Move tower 0, 1, 2, 3. Reversing these. Move tower. Well, this isn't. That's 0. We return nil. We print. Nil. Come back up here. Print. Come back over here. Nil. Print. Nil. Come back up. Here. Print. Come down here. Okay. I'm going to run out of space to run this tree. Are we getting the idea this is going to take a lot of steps? Lots and lots and lots and lots of steps. It takes exponential time.
And how do we know it's 2 to the n or 2 to the n minus 1? I mean, as opposed to just
As opposed to a lot. It is actually a lot. Because here we're building out this tree. And we're taking steps. So basically, for n is the height of the tree. And we're going to have 2 to the n leaves at the bottom of the tree.
okay.
Could you clarify how you built your tree? It doesn't really make any sense to me.
So what I did to build the tree was I looked and said there are 3 things under my else. The left branch is the first thing I'm going to do. The middle branch is the print. The right branch is what I'm going to do third. Okay. So the print here, we don't really need to consider that in terms of the time that we're computing. It's just printing out something. We can consider that as to be like our primitive plus or primitive multiplication. So effectively, at every step, we're branching out to 2 commands, 2 commands, 2 commands, 2 commands, which is why we have 2 to the n. How about space? How many delayed operations?
N.
I hear a very positive n, and we'll go with it. Why?
Because you're not actually expanding the tree out before you get to it.
Right. We're not expanding it till we get to it. The number of delayed operations is the height of the tree.
Delaying the expansion, basically.
So basically, what I was trying to do first was rather than creating the tree, I was trying to show if we went through this, we would basically cycle through this, then get to the move, and then would cycle through here. So I wrote it here as this branch, and then I wrote the 2 branches here, but we weren't actually evaluating these, and we wouldn't evaluate this until we came back up the tree. I just denoted it here because it made it a little bit easier for us to see on the board. Okay.
So
Yes.
to tie back to earlier, is this an example of a function that's both iterative and recursive, depending on which of those move towers you call? And then the interpreter will figure out. The first one, it'll make it recursive, and for the second one, it will make it iterative.
Is there anything iterative here? Are we using constant space?
In terms of the recursive or the iterative procedure call.
No. Okay. Recursive procedure. Calls itself, it's a recursive procedure. Iterative is a label that goes with process. Recursive process, iterative process. And that denotes how much space we're taking. If we have theta 1, constant space, it is an iterative process, by definition. In this case, we have delayed operations, therefore we are a recursive process. If we delay any operations, it is a recursive process. Both of these calls generate recursive processes. There's nothing iterative in either of those. They're both delaying some number of operations. Yeah. We'll go over this in recitation. We'll go over in tutorial too. That's really big. So, I never remember, but there are some monks who are charged with moving, I think it's only 32 discs. 64 discs, 8,000 years is the number. Something like that. They get to move 1 disc a minute for Towers of Hanoi, and when they move all the discs from one peg to the final peg, the world's going to end. And they've got these 64 discs. It's going to take something like over 8,000 years, I think. I think I heard 32 and 8,000, but some large number. Let me just put up a little bit of a chart for you on this one.
In that case, we're lucky that it's
Yes. Yes. It does mean if you run this code in the lab, you probably want to pick some small ends. Otherwise, you'll just be scrolling and scrolling and scrolling and scrolling and scrolling. You have a question? No, stretching. Okay, so let's look at, for values of n, 2, 10, and 100. And then this is going to be the theta of n. This is the n. So let's look at 1. Look at log 2n, n squared, which we haven't seen today, but hopefully we'll show an n squared in recitation. And 2 to the n. Okay, so if it's constant, this is going to be t of n. Could be space too, it doesn't really matter. But how many steps for constant if we've got n of 2? 10? 100? Good. Okay, log base 2 of n. Okay, these two, not so neat. 665 actually. But anyway, close. Would want to correct that, right? Wouldn't want that to be wrong. Okay. In n, it would be n squared and 2 to the n. This is the punchline. This is the kicker. It does seem fairly big, but which, if you calculate 1 billion ops a sec, will take. It is going to take, let's see, 3.5 times 10 to the 17th hours, or if we'd like to go in years instead, 4 times 10 to the 13th years, or if you prefer, 4 times 10 to the 11th centuries, which means you'll be sitting in the lab for an awfully long time. You probably don't do 1 billion operations a second. So this is just a little bit of a chart to show why do we care. When we start talking about analyzing algorithms, it's because it does matter. We want to write things more efficiently. We want to write them to run in less time. We want to think about if we're writing efficient algorithms or if we're writing things really badly. In the case of Towers of Hanoi, we don't have a choice. But when we're talking about writing our multiplication algorithms, we do. So do you guys have any questions? Go off, start problem 2. We'll go over this more in recitation. John will cover more of this, and we'll go over more of it in tutorial.